Hi students, in this session we are going to discuss the topic position of image plane. Here a ray starts from O dash and it goes along O dash A, touches the first refracting surface, gets refracted from there. It undergoes a series of refractions and translations, and finally, it undergoes one more refraction at B and emerges out, and the image is obtained at I. So I dash forms the image plane and O dash forms the object plane. So to determine the position of the image plane means, as usual, we determine the column matrix x2 lambda 2. But during this derivation, we obtain an important condition called the condition of the image plane or condition for obtaining the image plane. So let us proceed. The ray of light is starting from O dash, then reaching A. From A, it is undergoing one refraction, say one translation, and then one more refraction. Let us simplify the case here. So that first there is a translation happening here, then a refraction over here, a translation here, a refract and a refraction here. So mm, let us write down the system matrix in this case. Now the distance of the object from the refracting surface is represented by minus d1. It's minus d1 because on applying sign convention, the distances to the left of the refracting surface or against the direction of the incident ray are considered to be negative, and the distances to the right of the refracting surfaces are taken as positive. So the distance between I and the refracting surface d2 is positive, whereas d1 is negative. Now let us assume x1 lambda 1, x1 dash lambda 1 dash, x2 dash lambda 2 dash and x2 lambda 2 be the coordinates of the ray points at O dash, A, B and I dash. So at O dash it is x1 lambda 1, A dash x1 dash lambda 1 dash, B x2 dash lambda 2 dash and at I dash x2 lambda 2. So this x2 lambda 2 we have to represent it in terms of x1 lambda 1. So let us write the first equation. Now between O dash and A in this figure, from O dash and A, between O dash and the point A, there is a translation taking place. So let us write down the matrix equation, that is between O dash and A there is only translation. So x1 lambda dash is equal to T into x1 lambda 1, that is 1 0 minus d1 by mu 1 is 1 here because the ray is going through air, and 1. So 1 minus d1 0 1 into x1 lambda 1. So we got the first set of equation, matrix equation. Then from A to B, uh, from here to here, that is A to B means first there is a refraction over here, then a translation and then a refraction. So we can, uh, including all these three processes, we can directly write it as a system matrix here. That is x2 dash lambda 2 dash is equal to S into x1 dash lambda 1 dash, where S is equal to C minus D minus A B. We had written the system matrix in terms of the cost constants. Now lastly, between B and I dash, the last part, there is one more translation happening there when the ray goes from B dash to B to I dash, one more translation. So the last one, that is x2 lambda 2 is equal to x2 lambda 2, the final image position or image plane x2 lambda 2 is equal to 1 d2 0 1 into x2 dash lambda 2 dash. So we can replace all the others, that is x2 lambda 2 is equal to 1 d2 0 1 into x2 dash lambda 2 dash. What is x2 dash lambda 2 dash? It is x2 dash lambda 2 dash is c minus d minus a minus b into x1 dash lambda 1 dash. So I replace it with c. This is replaced with c minus d minus a minus b into 1 minus d 0 1 into x1 dash lambda 1 dash. C minus d minus a minus b into x1 dash lambda 1 dash, which is 1 minus d 0 1 into x1 lambda 1. That is the first matrix equation that we wrote. So we have got a system matrix here again, a product of 1, 2, 3 matrices. So you find out the product, first the last two, then the first one. So the product, when you do, you obtain it is in this fashion, that is x2 lambda 2 is equal to c minus d2a minus c d1 minus small d plus a d1 d2 plus small b d2 minus a d1 plus b into x1 lambda 1. Now let us write down the individual equations here. So x2 is equal to c minus d2a into x1 and this whole term into lambda 1. That is our first equation, and lambda 2 is equal to minus a into x1 plus a capital D1 plus b into lambda 1. So that is our second equation. Suppose the ray of light is coming from a point object lying on the axis. So suppose our object here is a point object lying on this axis. Then our image must also be a point lying on this axis. If the object is lying, a point object lying on the axis, then x1 must be equal to 0. Then as per that, the image x2 must also be equal to 0. So let us see what change happens in our equation. If we change it like this. That is, if we consider an axial point object, uh, then x1 is equal to 0 and the image plane is determined by x2 is equal to 0. So let us see what will happen to our equation 1. Uh, Thus, for the image plane, uh, we consider the first equation, this x2 becomes 0, x1 becomes 0. So, x2 is equal to minus c d1 minus d. These whole things come. X2 is equal to this term, long term, into lambda 1. But if x2 is also equal to 0, then either this or lambda 1 must be 0. Here, lambda 1 cannot be 0. So, who should be 0? The terms inside the bracket must be equal to 0. So, we get minus C capital D1 minus D plus A D1 D2 plus B D2 is equal to 0. This is called the condition of the image plane. The condition of the image plane. So to obtain the image plane, always minus C D1 minus D plus A D1 D2 plus B D2 must be equal to 0. Now this equation gives us the relation between D1 and D2. What are D1 and D2? D1 is actually the object distance and D2 is the image distance. Now, if this term is 0, then the corresponding image plane is obtained as x2 lambda 2 is equal to c minus d2a minus a 0 a d1 plus b into x1 lambda 1. Now, what did we actually do here? What did we do here? We applied a certain condition. That is, we obtained the equation for the image plane like this. We obtain the equation in the form of the matrix equation in this manner, and in the form of in the form of two linear equations in this manner. These are the equations for our image plane. Now we applied a special condition, that is to this to check the validity of this equation. That is, if my object is a point object, then x1 is equal to 0. So x2 must also be equal to 0. So first I gave x1 equal to 0, so that x2 is equal to this long term into lambda 1. But if x2 is also equal to 0, then either this one or lambda 1 must be equal to 0. Lambda 1 cannot be 0. So who should be 0? This term inside the bracket should always be 0. So whenever you have to find out the image plane, always you must take this term to be 0, because if you don't take this as 0, then this equation will not be valid if your object is point size. So this equation must be valid for all kind of objects. So when this equation becomes valid for a point object only when this term is equal to 0. So if you take this term as equal to 0, then this equation 1 will be valid for all sizes of the object. Um, so that is called the condition for of the image plane. That is, this term must be equal to 0. So now I rewrite my image plane equation as x2 lambda 2 into c minus d2a 0 minus a d1 plus b into x1 lambda 1. For then for x2 not equal to 0, that is for all other cases other than if the object is an axial point object. Other than an axial point object, for all other cases x2 will not be equal to 0. So what will be the equation for x2? x2 is equal to c minus d2a into x1, because the next term will always be 0. That term has vanished, so there won't be a second term. Okay, so for all other objects, the position of the image plane x2 is given by, so this is our answer. For the position of the image plane x2 is equal to c minus d2a into x1. Now I am going to write the magnification in this case. Magnification is either image distance by object distance or image size by object size. So x2 by x1 gives you the magnification. So x2 by x1 is equal to m is equal to c minus d2a. Okay, c minus d2a. Now we know that the determinant of the system matrix must be 1. So c minus d2a 0 minus a d1 plus b represents a system matrix. So its determinant must be equal to 1. So we get c minus d2a into a d1 plus b minus a into 0, that is 0, is equal to 1, or the product of these two terms must be equal to 1, or a d1 plus b is equal to, the single term is equal to 1 by c minus d2a, or it is equal to 1 by m, because we have found that m is equal to c minus d2a. So a d1 plus b is equal to 1 by m. So in terms of the magnification produced by the optical system, the system matrix equation of the image plane is given by x2 lambda 2 is equal to m 0 minus a 1 by m into x1 lambda 1. So this is the equation of the system matrix equation of the image plane in terms of magnification. So what all things did we do in this session? We found out, we considered a ray of light coming from the point O dash, getting refracted at A, then undergoing a translation, refraction, again a translation. We wrote down the system matrix for this entire system. After that, we wrote down the system matrix was found out, and the equation for the image plane was found out as x2 lambda 2, or the final refracted ray vectors representation in terms of a column matrix was given as x2 lambda 2 is equal to this whole system matrix into x1 lambda 1. And now I wrote it as two linear equations. X2 is equal to this term into x1 plus this into lambda 1, and lambda 2 is equal to this. Now I consider a special case, that is, if my object is a point object, then x1 equal to 0. So the first term vanishes. If the object is a point object, the image must also be point. So x2 must be 0. x2 is 0 only if either of these terms is 0. So lambda 1 can't be 0. So the term in the bracket is 0. This is called the condition for of the image plane. So it must we must always apply the condition of the image plane in order to get a valid position of the image plane. So, giving this term as 0 in the equation for the image plane, I get x2 lambda 2 is or in the matrix equation, I give I apply the condition of image plane, so that I get x2 lambda 2 is equal to this matrix into x1 lambda 1. And from that, I write down the position of the image plane when x2 is not equal to 0. x2 is equal to this term into x1. From that, I write down the magnification. Magnification is also expressed or is also found out by finding out the determinant of the system matrix. And finally, I write down the system matrix equation of the image plane is given by x2 lambda 2. The column matrix is equal to small m 0 minus a 1 by m into x1 lambda 1. I hope this session is clear to all of you. If you have any doubts, please do contact. Thank you.